Hello everyone, here is the work. The graphs included for the rectangular approximation for f of x is equal to 8 minus x cubed over the interval from 0 to 2, approximating the area here. Remember, you can check this with one of the two programs, or you're just using an online rectangular approximation calculator. Because remember, at the very end too, I wanted you to try this with different sub-intervals, increasing them along the way, just to see what the area was converging upon. And it turns out this exact area is 12. All right, so today we will take a look at something called a definite integral, and we will be able to evaluate this definite integral based on the concept of area. So at the end of yesterday's lesson, I just kind of drew a general curve, and we're going to go into a little bit more detail here. So again, I just want to make a sketch. We make it look like this. Call it y equals f of x again. And I want to show this from x equals a, which we'll kind of mark right here, to x equals b, which will be over here. And we're going to draw on some rectangles, but I want to use the right rectangular approximation method here. So if I were to draw on my first rectangle, so I'm going to call x naught, which is just our very first x value. I'm going to let that be a. And then I'm going to go over to x sub 1 here. So this is what I want to make for the right rectangular approximation. It'll look like this. And then we'll have x sub 2. Again, we'll go up and over. And I'm going to do this a series of times here. So somewhere in the middle, I'm going to have x sub I minus 1 and x sub I. And then at the end here, I'm going to have x sub n minus 1, and b is going to be called x sub n. I'll just show some dots here to show that we're going to have some rectangles in there. So each rectangle is going to give me an area. I'll call this the first area, second area, call it the ith rectangle here for the ith area. And then I'll have my last area right here, so a sub n. The more rectangles used, what we noticed in that one Inspire doc, the more rectangles used, the better the approximation is. So one way I'm going to represent the total area, it's still an approximation at this point, is going to be the sum of the areas. So the area of the first rectangle plus the area of the second rectangle plus the area of the rectangle at some point in the middle, and then plus our last rectangle. So if you recall, also at the end of the video from yesterday, I used sigma notation. So we could write this as the sum as I goes from 1 to n of all of our areas. We'll call it a sub I. Well, to replace the area with an actual formula, so write the summation notation. Again, the area of any rectangle is going to be the width times the height in this case. So every width, I'm just going to write this as a delta x sub I. And then the height is f of x sub I. Because delta x sub I is just indicating the base or the width and then f of x sub I is the height of each rectangle. It's still an approximation at this point. How we're going to change this into figuring out the exact area, we're going to bring in limits. So the total area here is going to equal the limit as n increases without bound of the summation as I goes from 1 to n of this delta x sub I times f of x sub I. Another way to write this, kind of write this off to the side, is that the total area could also equal the limit as delta x sub I goes to 0, meaning the widths of the rectangles are getting skinnier, more narrow, so we could fit more rectangles in there. And again, of the summation as I goes from 1 to n of delta x sub I times f of x sub I. Well, we're not going to work with this notation here. In fact, we're going to replace this notation with something that's a lot simpler. So we have a new symbol now, and it looks like this. So replacing this entire limit as n approaches infinity of this summation here is, and it looks like a very stretched out s, but it's actually called the integral. So now we can say the exact total area is equal to the integral, and then we put our interval values here. So if it's over a closed interval from a to b, we say a to b this way, of f of x, that's representing the height of each rectangle, and then instead of delta x, we're going to write dx. So again, f of x is the height of each rectangle, and dx is the width of the base, which is delta x. All right, so again, our goal was we are going to evaluate definite integrals based on the concept of area. So we're going to make a sketch of a graph here to help us find this. So an integral is related to area under a curve. So let's go ahead and copy down example 1. And we're going to kind of break this down into what is f of x. So remember, it's the integral from a to b, our total area, is the integral from a to b of f of x dx. So in this problem, f of x is the 6. So we're going to go ahead and make a sketch. We're going to graph the function f of x equals 6. So that's just going to be a horizontal line right here. So this is f of x equals 6. But we're only going from x equals 2 to x equals 5. So if I draw a line down here, that's x equals 2 to x equals 5. And then I want to find the area here. Well, we created a nice figure, nice geometric figure, so we can turn this into just an area formula. So this is the same as just the length times the width here. So from 2 to 5, that's going to be a length of 3. And then our height is 6. So we're really getting 6 times 3, which is 18. Now, I wasn't really finding the area. I was only using the area to help us evaluate this integral. So I'm not attaching square units here. We're only using area to help us find the value of this integral. All right, we're going to do the similar process for number 2. Here, our function is what? 4 minus 2x. So we want to graph this. And again, just a nice sketch. It doesn't have to be precise. So we have our line here for y equals 4 minus 2x. Now notice it's going from 0 to 2, so I'm only shading the area from x equals 0 to x equals 2. I don't go below the x-axis. Now we formed a nice triangle, so this is going to equal the area of the triangle, which is 1/2 the base times the height. So our base has a measurement of 2, and our height is 4. So here the integral is just equal to 4. All right, so for example 3, we have the integral from -1 to 1. Here our function is 1 minus the absolute value of x. So notice I do have this graphed off to the side. We know that this is going to open down. So we can say like we're reflecting y equals absolute value of x, and then we're shifting it up 1 unit. But now if you notice, we created one large triangle, or you can look at this as 2 separate triangles. Let's do this as just one large triangle. So this will now become 1/2. Our base is 2, and our height is 1. But you can pause the video to get the sketch of this graph. And this should just equal a 1. And now in example 4, our function here is the square root of 16 minus x squared. So do you remember what that graphs? It should graph a semicircle, the upper half with a radius of 4. So we are trying to find the area from x equals -4 to 4. So we're going to use the formula for area of a circle, but cut it in half. So it's going to become 1/2 times pi times our radius squared. And this gives us 8 pi. So what's nice is if we have a nice geometric figure formed from our graph, we could just use the formula for area of that figure to help us evaluate the integral. That's not always going to be the case, and that's what we're going to eventually move on to for upcoming sections throughout Chapter 5. All right, so everything I'm giving you right now, you'll have over the weekend to work on this because your test is tomorrow. So in addition, I want you guys to still continue working on the AP practice problems I assigned yesterday. I was on pages 7 and 8, and then the free response question as well on page 121. Also add to that on AP page 156, number 5, that's another free response question. On pages 10 and 11, 36 and 38. And then out of the textbook on page 267, which I'll have all of this section scanned in for you, 1 through 29 odd, calculator. And to say calculator is okay for these problems here. Okay, take care. Let me know if you have any questions.